All right, let's talk about something that sounds like it's straight out of a sci-fi movie, but I promise you, it is 100% real. We're diving into the delayed choice quantum eraser experiment, a setup that seriously seems to mess with our whole concept of time itself.
You know, at the core of this whole thing is a paradox that has been bugging physicists and philosophers for years. The results look like, and I mean really look like, an action you take right now can somehow change something that's already happened. It feels impossible, but hey, it's a real experiment with real data.
And that leads us to the one big juicy question. Can the future actually reach back and change the past? Now, if you just glance at the results of this experiment, you'd be tempted to say, oh my God, yes! But hold on, because what's really going on is so much more subtle and, honestly, a whole lot weirder.
So here's the crazy part. Imagine you detect a particle, okay? You write down where it landed, it's done, it's in the past. Then, nanoseconds later, you do something to its entangled twin, which could be far away. And somehow, that choice you just made seems to decide if the first particle acted like a tiny bullet or a spread-out wave, back when you first saw it. How is that possible?
And just to be clear, I'm not being dramatic here. This is how scientists actually talk about it in the literature. They say it appears to be retroactive, that a choice now dictates a reality back then. So what we're going to do is play detective and figure out what's behind this incredible illusion.
To solve this mystery, we can't just skip to the end. We've got to get our quantum toolkit ready. We need to go over the basic rules of the game, the essential clues, before we can crack this thing wide open. Think of it as our pre-mission briefing.
Okay, rule number one, and it is a big one, wave-particle duality. A tiny thing like a photon can act like a particle, a little pinpoint of stuff, or it can act like a spread-out wave. And the wild part is, it decides which face to show us based on how we're looking at it. It's like it has a split personality.
And that leads us straight to our second clue, which is crucial: complementarity. Think of it this way. You can either know where the particle went, its particle nature, like which specific path it took, or you can see its wavy nature, that cool interference pattern. But you can't ever know both at the same time. It's a fundamental can't have your cake and eat it too rule of the universe.
And for our third clue, we have the magic ingredient, entanglement. This is that spooky action at a distance Einstein talked about. You can link two particles so they become one single system. You measure something on one of them, and the other one is instantly correlated, no matter how far apart they are. It's not sending a signal, it's just they're connected.
So let's just nail this down. If you want to see that classic wave behavior, the interference pattern, you have to be completely ignorant about which path the particle took. The second you know which slit it went through, poof, the wave pattern vanishes. All you get are two simple clumps. It's the information itself that seems to destroy the waviness.
Okay, we've got our rules. Now let's head to the scene of the crime. We're going to trace the photons step by step through the experiment and see exactly how this mind-bending paradox gets built.
Here's the journey. A single photon goes through a double slit. Then it hits a special crystal that splits it into two entangled twins. We'll call them the signal photon and the idler photon. The signal photon zips right over to our main detector. But its twin, the idler, gets sent on this long, winding detour where we're going to mess with it, either find out its path information or erase it.
And this is the absolute key to the whole illusion. That signal photon, it hits its detector a full 8 nanoseconds before its idler twin even reaches the part of the experiment where we choose what to do. Think about that. The first photon's journey is over. It's already in the history books, before we've even decided what question to ask its brother. So, the stage is set. The paradox is in place. But now we get to the part of the story that is almost always left out of the popular explanations. This is the big reveal. This is the smoking gun that unravels the entire mystery.
So, I have a question for you. Given all this weirdness, what do you think you'd actually see on that main detector screen in real time? As all the signal photons are hitting it one by one, what's the pattern? Is it a wave pattern? Two clumps? Does it magically flicker back and forth as choices are made in the future?
The answer is a totally boring, featureless smudge. That's it. When you look at the total pattern from all the photons hitting the screen, all you see is a big, blurry blob. No interference pattern, none. And that, right there, is the key to solving this whole thing.
This is so important. Nothing is physically changing in the past. That screen never shows an interference pattern that magically disappears or one that appears out of nowhere. The physical reality on that screen is always the same boring clump. Why? Because the path information is always, in principle, out there, available from its entangled twin.
Right, which leads to the next logical question. If all you ever see on the screen is a smudge, then where on earth do those famous interference patterns that define this experiment even come from? If they're not physically there, where are they hiding?
The secret is a technique called post-selection. The patterns aren't physically created, they are revealed statistically. After the experiment is totally over, scientists take the data from that smudge and start sorting it into different piles. And the pile a photon's data goes into depends entirely on what happened to its twin. It's just clever data analysis, not time travel.
It's really cool how it works. They can tell the computer, okay, only show me the hits from signal photons whose twins told us which path they took. And boom, that data forms two clumps. Then they say, all right, now only show me the data from photons whose twins had their path info erased. And what do you know? A perfect interference pattern just emerges from the data. But here's the kicker. You add all those separate, sorted patterns back together, and you're right back to the original smudge. The patterns were just hidden correlations in the data all along.
So, with the paradox solved, what have we actually learned? What does this incredible experiment really tell us about the nature of reality? Because it doesn't demonstrate time travel, but what it does demonstrate is arguably much more profound.
So let's just be absolutely clear. The verdict is in. The experiment does not show the future changing the past. There is no retrocausality. There is no information being sent back in time. The fundamental laws of causality are perfectly safe.
So what's the real lesson? First, the past is never changed. Second, those patterns are just statistical ghosts we find by sorting the data after the experiment is over. And you need to use a normal slow cable to send the information over to do that sorting. Ultimately, this experiment isn't about time travel, it's about the deep, weird nature of entanglement, how two particles can act as a single, unified system whose complete story can only be told once all the information is brought together.
John Wheeler, the physicist who first dreamed this whole thing up, put it perfectly. He said, "The past has no existence except as it is recorded in the present." Now, he didn't mean we change the past. He meant that the past of a quantum particle was never a single fixed story to begin with. The only story we can tell about it is the one that's consistent with all the information we've gathered from the entire system, right here and now.
And that leaves us with this final, truly mind-expanding thought. The quantum eraser doesn't show the future changing the past. It suggests something much stranger, that the quantum past was never one definite thing. It was a superposition of all possibilities, a tapestry of potential histories, just waiting for a complete measurement of the entire entangled system to tell us which one of those stories is consistent with our reality. And if you ask me, that is a far more fascinating mystery than simple time travel could ever be.